Checking audio. 1, 2, 3. Checking audio. 1, 2, 3. Okay, audio checked. We are good to go. Ladies and gentlemen, welcome to the stream of the Discourager of Hesitancy. We're doing a little bit of beginner programming. These lectures are not refined. Preparations have been rushed. So this is not like the final form of the lectures. I'm more concerned with, am I getting the structure of what I want to say correct? There are areas where I haven't explained enough, haven't given enough examples. There are areas where I should split whole lectures in half. But I like overall the structure. So I think with some refinement, this lecture series could be pretty good. And our first big project is to build a virtual machine, which is a simplified model of how a computer works. Very simplified. And that is something you should be able to do on your own, even as a beginner, piece by piece. I think a lot of programming teaching starts with too many small projects. There were a few small projects in earlier lecture, and I need to spread those out a little better. But at this point, I think if you get to this one and have done the previous assignments, you should be able to build a virtual machine piece by piece. I'm not going to post the code. You need to type it in yourself. But I do think you should be able to build a virtual machine from scratch if it's simple, which ours is pretty simple. One thing I hadn't done before starting yesterday was to define our instruction set architecture. And so I spent some time fleshing that out. Now there's this document, which I will link in the YouTube video when I upload it, which gives instructions on how everything is structured and how it fits and so on and so forth. So we should be able to use this as our design document for our virtual machine to some degree. I've made some changes since I was looking around things, and so I think we'll go implement those changes, but we're just going to take a look at this. So some of our operations are going to be able to handle multiple types, so you'll always be able to pass in a 4-bit type field. And for now, all we support is integers, signed integers, unsigned integers, and floats. As we develop our understanding of programming and make our computer model more complicated, that will change. But signed integer, unsigned integer, and a float. Those are our types. We kind of stumbled upon this yesterday. Sometimes we want a field that can be either a register or a value, like in a constant, a predefined compile time value. So this is how we do it. We check the most significant bit. If it's 1, then we get values between 0 and 127. Unless it's signed, then we subtract 63, so we get values between negative 63 and 64. Okay? So that's that. Otherwise, it's just a register, and it has to be between 0 and 7. So we've already used this a little bit. Now it's more clearly defined and documented. So if your multi-mode field, MMRRF, it's an F, multi-mode field, means it could be either register mode or immediate mode. There we go, MMF, my bad. Memory addressing, we are going to deal with that a little. We've already dealt with it a little bit, which is kind of where we end up with these multi-mode fields. Basically, you always have 2 parts to the address. They are multi-mode fields. So you can have a register plus a constant, register plus register, constant plus constant, and constant plus register to compute an address. So lots of flexibility there. Then we have the actual instructions. We've already talked about this. Top 12 bit, the most significant 12 bits are the opcode. Everything else are the parameters. So if we look at our no op, those 20 bits are just wasted, completely unused. Our print we talked about, but now it's documented. First we get the register that we're supposed to print out, and then we get the formatting for it. For now, we're going to start with only 5 different actual formats. We may extend that a bit. Having integers, unsigned integers, floats, those are all fairly standard. Character, since our registers are 32 bits, we only print the lowest byte. So if we want to print strings, there's a couple different ways we can go about that, which we will explore today a little bit. Hex values. Sometimes it's easier for me to see what's happening to the bits if I look at it as a hex, because then it's more like binary. Each digit in a hexadecimal number is 4 bits, and so we can understand a little bit better about the bit structure of things. Any other value we get for our format, I'm going to just print out the hex value. That's the plan. So I know I have to make some updates for this. I've changed it a little bit from what we actually implemented yesterday. Halt, same as usual. We return this code. That's our exit code. Nothing too interesting. I put the size of the fields and a mask off and a shift offset. So if you want to get this value out, you take the whole instruction, and it with this, and then bit shift it that much to the right. Load, immediate mode, meaning we get a 16-bit value, and we shove it into register A. Not too complicated. We already had that working yesterday. Load from memory. We have a register, that's the destination register, but we also have address part 1 and part 2, which we talked about up in the addressing. So when we say address, these are multi-mode fields, MMFs, and they are added together. So that is all documented right here. Multi-mode fields, we can get either a value or a register number, and then we add them, and that gives us our address. So we're not going to duplicate our documentation there. So that's our load. So it gets this address, and then shoves it into register A. Store goes the other way. We take the contents of A and shove it into the address. Again, size, mask, bit shifting, all that's just figured out and done for you. We are today going to add arithmetic, bitwise, and comparison operators. So that'll be great. And that, trying to decide, there's a couple different ways we can go from here. This is where me doing this lecture series with very little prep shows me the weaknesses of it. I need to, maybe there's a better order I could have the virtual machine developed in. So when I do an actual lesson plan in the future, I'll be like, okay, here's the first thing they have to do, here's the second thing they have to do. So they can be turned into like little mini assignments, little checklists. If this works, then the next part is the next part. Like break it down. A beginner looks at a lot of scope and freezes up, but the more experienced you are, the more you can see the small pieces that have to happen in what order. I tend to discover those orders, but now that I've gone through the development process, I think documenting how I broke it down and what order things should be implemented in is something that I should spell out more in future versions of this lecture, of these lectures. So that is a thing that we'll have to deal with. And that is pretty much it. So we've got a whole bunch of operators I've worked out. Most of the ones we need. There will be a few more tomorrow that we'll have to deal with, and we will talk about those when we get there. But here's the deal. I'm print. I've changed the way it works. I put the register first and then the format. I think in our code it's format first, then a register. So we're going to make a few changes here and there. We've also changed the opcodes a little bit. The print is now FFE, and halt is still FFF. We've actually put the instructions at the other end, 001. So we have some changes to make. So let's go make some changes to our code and make sure we don't break anything. So let's bring up Emacs. So step 1, we're going to change these opcodes. That'll be pretty straightforward, I think. Let me hide ye old browser. And we define all of our opcodes somewhere. There we are. So we have no op, we have halt. Let's see. Load I, yeah, so I've just decided to build most of our code this way. 1, 2, 3, 4. Print, actually, I've moved up here next to halt. It's not really part of a normal flow, it's an output thing. Okay, load store. Okay, we are going to today also add, and we're just going to add these all right here. Add, subtract, I'm just going to scroll through real quick and add them as we get there. Multiply, divide. Multiply, divide. So these are like memory and program state and output. It's not really very well defined here, but this is definitely arithmetic. That's right, multiply, divide. Okay, what else do we need? Multiply, divide. We're going to have bitwise operations. And OR and XOR and not. Bit shift left and bit shift right. Bit shift left, bit shift right. I think that's all of the bitwise operations. Oh, right then left, my bad. Then we need comparisons. We need to be able to compare things. So we go greater than, less than, greater than, equal to, less than, equal to, equal, and not equal. Those are the ones we need. Go back down to that. Okay, and I think that's all I've got in the instruction set architecture document. Not equal. Okay, so we're going to implement all of these today at some point. Let me make sure that the opcodes are actually correct. Add 4. So in theory, 5, 6, 7, 8, 9, A, B, oops, C, D. So let me find. Or was not. I'm just like spot checking. BSL bit shift left was. Oh no. BSL BSR. Bit shift left was B. Where's my not? There's not. Opcode A. I'm off somewhere. Division was 7. Yep. And is 8. OR is 9. XOR. I forgot an XOR. XOR is A. Okay, not is B. I got it wrong in my document, so let me just change that real quick. B. Not is B. And bit shift left is C and D. Bit shift left C. Bit shift right is D. Bit shift left, bit shift right. And this one is an extra. So we go straight to greater than. It should be E, right? E, F. I kind of want to put equal, not equal first. E, F, 1, 11, 12, 13. That's probably better. Let me go reorder it in my document. Like I said, I'll post this document after today. So we're putting equals before greater than, less than. So instead of D, equals is E. F for not equals. Greater than would be 10 in X, obviously. $11. $12. Lecture, yeah, kind of. We're sort of at the point of, we've done some basic lectures. Like I said, needs a lot of work, lots of refinement, needs more examples. But the overall organization I'm pretty happy with. We've kind of talked how to learn C, how to learn programming, what the structure of a program is, what words are that we need to know, like format and encoding and things like that, what a bit is. So we're kind of at the point where we need to understand the computer. So part of the first major assignment is to build a DoH virtual machine, a discourage over hesitancy virtual machine. So I'm putting that together and refining our documents as we go. So the first like 4 lectures are mostly informational. I should spread out the assignments a little better, do things better there, but then we're at the point of you need to build a significant piece of software, which I think a virtual machine is a good place to start. So that's where we're at. We're building a virtual machine. Yesterday we did all the register, load, and store, no op, halt, print, that stuff. Today we'll try to get through arithmetic, bitwise, and comparison operations. So yeah, because I think if you start with a very, very simple virtual machine, it's not too bad, but then you add complexity as your understanding of the computer and programming extends. And then I kind of have this notion that it's a 3-part series. One where we build up this virtual machine and do problems with it, all in binary coding, right? Bit code, or byte code, I guess. And then the second series is we don't want to write byte code, so let's make a compiler, and we can do a very simple compiler. Does not have to be fancy. And then once we get through that, we go through like an optimization phase of let's make the virtual machine faster. Let's make our compiled byte code faster. Let's make, let's study performance. So kind of a 3-part series. I don't know how far we'll get, but I think the structure of the lectures is coming together. I just need to, I'm taking notes on how to fix what I've got. Problem when I'm trying to do one lecture a day. It's not much prep time. So yeah, let me know if you have any questions or suggestions, or if there's something I missed. I know there are things I missed in earlier lectures. I feel a little bad about that, but like I said, I'm sort of develop things incrementally, iteratively. So yeah, I've got this here instruction set architecture document we're kind of working through right now. Explains how the instructions work, what the fields are. If you print, we need to register, then we need to format how to print it out, that sort of thing. Here's how you halt. Here's the return code is stored in that address. And that register. Actually, maybe. So here's a thought. Sometimes when I want to halt, I don't want to load a value into register. I just want to return an actual value. So maybe we change this up a little bit to take one of the multi-mode fields. It's probably better that way. Delete that. Now that I'm thinking about it, we need our 16 columns back. 10. Lame. No. Really? Huh. Maybe we just steal a new table. Delete the old table. Halt 31, 0. So yeah, doing a little bit of, where's the split cell? This is 1 byte. And this is 1 byte. Then these 4 are all going to be blue. Wrong blue. Still the wrong blue. Yikes. And these are all merged. Oh, come on. We're just changing up our virtual machine definition as we go here while I think things through. So this is going to be a multi-mode field. And then the rest of this is unused. Come on, unused. Not that one. These ones. Unused. We called it something, I thought, somewhere. Let's see here. Yep, just unused. All right. Which means this whole table goes away. Delete table. This is our new specification for this one. Opcode. So this is FFF. Multi-mode field A will be 8 bits long, starting at 12 going to 19. Means we have to mask off 1 byte. We only have to bit shift it 12 bits. All right. So we need to update halt and print. We changed the way those work now. So it's time to go to the code. Let's go grab these and just throw them in places. So this is where we get our instruction. So this is the fetch on our program. We get the instruction out of memory at our program counter. We decode it, so we get our opcode. which tells us where to go. Now, okay, I already messed that up. It's okay. All right, let's try this again. Case. Delete 1, 2, 3. Alt handler equals DoHVM opcode XYZ break. We're just shoving these in. It's not going to do much. Maybe we call these bitwise and bitwise or bitwise XOR, bitwise not. Maybe we'll make a logical chunk eventually. Just lots of different ways we can attack this design. Int alt load and store. Int alt load store. Registers in memory. Okay. Bitwise, 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 shift left, band, bore, vexor, but not. I'm going to change that in my instructions set. So our naming is accurate. Add, subtract, multiply, divide. Okay. Bitwise and bitwise or bitwise XOR bitwise not. We will eventually want logical versions of these as well, but not yet. Okay. Bitwise and, oh yeah. So we need to create some, oh, right here. Okay, perfect. 2, 3, 4, void, DoHVM op case. Shove it in for now because we can get through this quick. There we go. All right. So we're getting registers and memory. Arithmetic. Bitwise operations. Comparison. There we go. Okay. Neat macro. Thanks. There are some fun little macros out there. All right, let's see. So make some more macros. Ready? Here we go. Oops, F3. We're going to search for parentheses. Go back one, backward, forward. Now we're going to delete the white space. Delete the semicolon. Put in brackets. And boom. I'm going to improve it slightly. We're going to center after a run. Boom. There we go. That's better. Perfect. So we've subbed out functions for these. This printing thing. One thing I want is to move the printing of an operation out of the function that's actually executing it. All right, we're gonna do, I need a function for that. I think DoHVM print instruction. And it's very similar to everything else, which makes me a little sad. We're gonna get our opcode. Extract field, I think, is an important thing we will want. So we'll come down to that. Let's see, we're not doing anything fancy. Search for colon, backward space, mark, forward word, search for X, Y, Z, and paste, and down case. Piece of cake. All right, easy to read code, very nice. Print. I think I put print up here. Maybe I should just change the order completely. Maybe no op, alt and print. When I'm looking at things, I try to order things in an order that makes sense in my head. So I think it's alt, then print, then no op. Okay. So this is very similar to the way that a CPU would work. It fetches an instruction, so it looks in register 0 to get our program counter. Checks. We check bounds because it's a virtual machine, so we need to check that. In hardware, it would be done differently. It's fine. Then we get the instruction out of memory at our program counter. We decode, so we get our opcode and then execute. So when we're decoding, we get our operation code, and that tells us what function will handle that instruction. Then we execute that function. Then we advance our program counter. Easy peasy. I'm going to, so we're doing this print thing. I'm going to grab all this. Print instruction. default. Okay. Here we go. No op is the easiest. Oh, we also want program counter if we can. That's the thing I have to change. Print instruction. We need the program counter and the instruction. Program counter, then instruction. Whoa, come back. Just trying to generalize things a little bit. Program counter. There we go. We're going to go up to 4 decimals wide. Right now our memory is less than 1,000, so that should be fine. Then given the opcode, we print F, the name of it basically. Come back and fix all of this. Let's see. We do macros in small pieces. It's not that bad. Okay, that's one. Next part. We're going to search for a poem, get the word, search for new. There we go. Now, invalid op. Okay. So here we get our instruction, we get our opcode. Here we can print our instruction. We can do there. That would probably be better than what we're doing now, I think. If, oh, interestingly, I'm going to change this a little bit. Print instruction. I'm actually going to just take the VM itself. DoHVM. PC equals -1. I think that's more correct. Print instruction at there. Okay. If our program counter isn't passed into us, if it's less than 0, our program counter equals VM registers at 0 unsigned. Then we get our instruction. Equals underscore VM memory at PC, just like that. So we can either pass in the program counter, or we can use what's in our VM. Yeah, I think that's better. Okay. Halt. Let's see what we've got here. So you see this reg. I kind of want traction as a separate function, or extract mask and shift. This will return instruction and with our mask bit shifted by shift amount. We'll see how this goes. No op does nothing. Wait, print instruction. Do print equals 0. If the VM is running and the VM is verbose, okay, so if I pass in an actual program counter, I'm saying I really want this to print out. You don't check verbosity or whatnot. If we're not running and I pass in something, do I care if it's running? I guess not. If not, do print return. That's probably good enough, right? If not verbose, I think that's simpler. Mutate T register equals, we'll call this register A, equals extract this mask and then shift. register A. Extract with mask and shift. Register A. Extract mask 0 shift. I think. We do this. We have to declare these types outside of switch if we want to use them this way. So uint 8t, register A, register B, register C. I know those are things we will need eventually. We need a uint 16 value. Value stored in register A. There we go. So we put all of this stuff in this print. I think it does make enough sense. So load M. It's the next instruction. It does this whole thing. So the first one we do is we need the register. We need address part 1, address part 2. We're just doing a little bit of refactoring. I think it'll clean up things nicely. That was address 1. Here's address 2. I think what I want to do is in MF, we can change extract to just field. Or, yeah. So this is the thing we're going to want to do semi-regularly, is either extract the value or extract the... So I think we just have to make that a function. I don't think it's macro appropriate. Multiple mode field. And all we really need then is, was it registered or not returned out? And then uint 8t. Oh dear. Nope, this gets more complicated. Shoot. I'm trying to think of a simple way to get everything I need into one function. These can be signed or unsigned. Signed multi-mode field. And an unsigned multi-mode field. Result equals 0. I'm going to do this in a second. So here's the point. When we load, we have to ask ourselves if this is true. We do that. Okay, so let's go down to equals. Oh. There we go. If the contents of MMF and DoHVM mode register if result and not this bit, dot signed integer minus 63. Return the result. I think that's basically all we need. Except for here, no, not where that happens. MMF, MMF. We need to do some checking and fail out if we do things wrong. Okay. If the contents of MMF are less than or equal to, are between the number of registers, which if I remember right, is a thing we just have somewhere. In case I want to change it in the future. Known registers, registered count. Yes. the if it's a register, make sure it's a valid register. Do I pasted a bunch of stuff, didn't I? Let's see. Done. DoHVM error. Otherwise, we do that. Contents of our multi-mode field is taken as a register. Register values. Oh no, register number. Wait. If it's a register, we strip off the register bit. Otherwise, it's a literal value and we just take the offset there. Error, VM error code error message. Oh, we don't have the VM at this point. Shoot! Huh. Guess I'm trying to extract out some of this logic into one place so I never have to write it again. Unfortunately, we need the VM so we can give an error if we need to. Okay. Is this a register? If this is a register. And a valid register. So we need the VM, we need an error code. Invalid register found in multiple mode field. Okay, I think that's that. The contents of multi-mode field. Okay, does that simplify things enough for me to use this? I think so, because I really don't want a bunch of error checking all over. Basically, the only real difference is that do need the VM. Because DoHVM error means it. Where is that written? I have an error code, I have an error message. We shut down the VM. Print instruction, blah, blah, blah. Okay, so in theory, load M. Maybe I'll take address 1 and 2. Come back to this printing nonsense here in a minute. If DoHVM unsigned multi-mode field of address 1, if it was a register, then we get the register value. There's something here. It was like address 1 and 7F. But this all goes away. It's a 2-liner. Same thing happens for address 2. So if we do this all right, then we're good. I think that's much more concise and does error checking. Okay. Okay, I think we replaced all of this with this, so now we can log what we've got in print instruction. Okay, RA is a thing. So address 1, address 2 we'll have to define. Address 1, address 2. A large part of this has to do with separating the printing from the execution itself. Okay, so load into memory. the register, register A, into memory at address something or other. Now, if this is a register, then we're going to do $, address 1. Otherwise, it's not a register, it's a constant. Okay, in theory, that should print out a load instruction, whether it's registers or not. There's a store instruction, which is actually going to be very, very similar. Let's just copy paste this. Memory. Square bracket out to $U, which is register A. Okay, address 1, address 2, and the field. Square bracket 1. Okay. We'll start with the most complicated. So node M here. This shall be much simpler. Store is going to actually look a lot more like this now. The logging will be handled elsewhere. We've replaced all of this junk. And now the memory itself is assigned from a register. Perfect. Okay. All right. So in theory, we should be able to execute a program. And maybe it will work. Oh, we've changed things though. We've changed the way print works. We basically flip-flop these ones. Register output as halt. We changed a bit here. Halt. Register probably a bit shifts. 12 now. Oops. It's got 12 and 4 is 12, yeah. So this whole add halt thing. Register, there we go. What else have we got here? Anything else that needs to be done? Let's just see what happens. Make, okay, we made some errors. but we just did a semi-major refactor, so not too big of a deal. All right, so line 39. All right, now we're getting down to it. Okay. Register undeclared. This is now our Sunday. Halt does not need a print statement anymore. Oops. That's argument 1. Incompatible player type. Okay, that's fair. Load field. What? Oh, right. Okay. That is a uint 8. Should be correct. Let's see here. Uint 8. T expected. DoHVM. Oh, right. VM. I forgot the VM. I don't think about the VM because it's only really necessary for printing the error out. Register. That's probably called RSA now. We have a copy paste of that same error here. Unknown type. Let's see here. Address. Okay. Too many arguments. Oh. VM register 0. Okay, it technically compiles, but does not mean it runs correctly. So if we run this, invalid register found in multiple mode field. In instruction 2, add load store. So I should have a register 1 and an immediate mode 13. See what our error checking looks like. first. This is a store, so that'll be a U. So it's this one. Oh. If it's not in this range, this checks for correctness, not for incorrectness. Not. There we go. That'll fix that error. The logic was backwards, and we've got the same output. Now, if we go to main and we turn on verbose, I just want to see how that turns out. Okay. Oof. Well, definitely a couple of mistakes have been made. Print instruction. That'll make it a little easier to understand what's going on here. There we go. Load, nope, let's see here. Loop, load I. So I probably have a hard-coded end of line there. Let's go with the load I version here. Yep, there it is. Try to make our output formatted nicely. 1, 2, 3, print. Oh, okay, so these ones not yet been removed. So the print to print, something we need to copy over. Load I. Oh, yeah, so this print didn't put the new line, that's fine. So this load I is fine, this print, yeah, so it's just print now. Load M and halt needs an update to its printout. This load is backwards. Store and loader backwards. is. Oh yeah, field. Or field out of here. Instead of reg, our print is backwards. Now it's backwards. So I'm going to swap those. Oops. Format. Okay. Okay. Print. There we go. So this is format. Register A. Except I think it's all backwards. Register to be this one. Format. Is this one. So we swapped it. All right, and then $sign B. Register A. There we go. So that should fix that one. Just trying to get to where we were yesterday, basically. So there's the star, load, print. There's the new line character. This print is a mess. Why is that one a mess? $1. So this should be hex. So let's go see what that's all about. Oh, print types. We've got one more than I thought. Char and X. There we go. print as hex this thing. There it is. Print a character, again, new line character, load, load. This is wrong. That's wrong. Okay, we're getting there. So load immediate looks fine. So this one, register a address 1. Address 1. Oh, we have some copy paste problems here. Address 2. Address 2, address 2, address 2. Alright, I think we're getting there. I actually want to do a print multi-mode field. I think so. All right, address 2, 2, 2, 2. Our multi-mode field. This is going to show up more than once. We're just building up all the pieces we need. Okay. If DoHVM this thing. Oop, not that one. This stuff. Okay. Not print the space. These are not address 1. There's our space and a plus, I think. I think that's much cleaner. Address 2. Almost there. Run that. No upload I. Store print character. Load a new line character. Print the character. Print the value as a hex. Print a character. New line. Load 42. Load. Okay. Register 42 is 100% absolutely wrong. It should be 42, but I want the content of the register. I just want the register number. So that is probably an issue in here. Don't need that. What is this? There we go. Load into 2. Memory at address 1 plus 13. All right. Our print and our execution now line up. Our print now handles everything correctly. Our halt, interestingly, we could just check the halt. We're not doing, maybe we just halt with 13 as a constant instead of a register. Just to try it out. Echo $10 question mark 10. Oh, our halt isn't printing correctly either. Let's put this one back the way it was. We'll put them both in, even though it doesn't matter. Now we can comment one out or the other if we want to. DoHVM.c print instruction halt. So with the math of that and an offset of 12 bits, print UMF. Oh, interesting. Load. Okay, load is from memory to a register. And store goes the other way. $sign. I don't know why I got that print so wrong, but that's okay. You get good logging now. It will save you a ton of work later. Store. load a constant load. That looks correct. It's just this store. Store. Oops. There we go. Fix that one. There, store whatever's in 1 into the memory address of 1 plus 13. That's great. Halt $2. $2 should hold the number 42. So question mark 0. That should not be 0. Halt $2. Alt $2. Oh. Maybe we didn't update this function enough. There's our field. Multi-mode field as an int 8. This will be a signed MMF address of multi-mode field. Multi-mode field signed integer. Field. There we go. That should fix that. Boom, echo, don't type question mark. Now it's wrong. Wrong. That should be 42. Why is it 201? Alt $2. Oh. F. There we go. Oh, and it's not 16 bits, it's 12 bits. Echo 42, there it is. Now if we go to main, and we switch it to just return number 13, that's 206. So something's still wrong. Oh, because we subtracted. Hold on. I know what's going on, but now I'm being distracted. I need to take a restroom break. Be right back. Just a minute. Here we go back to it. So we're Alt 13. Okay, so we need to actually change that just a little bit. Plus 63. We can make this simple enough. Add halt. If this and our register otherwise our register plus 63. Okay, that's still wrong. That's a halt 0. I thought assigned assigned multiple mode field. If strip off the bit, if the register is correct, blah blah blah. Otherwise, subtract 63. How we can get values from negative 63 up to 64. If it's a register, we're just oh. There we go. If we're not a register, we have the offset, otherwise it's just good to go. There's our 13. There we go. Then we go back to register based exit code. And it should be 42. Perfect. Okay, we're done. Phew. Okay, so print halt. Those have all been re-architected. Load. The relative values are all relative. Oh. That's actually a good question. Load and store don't have offsets. So that's actually fine. Cool. I think, I mean, we could also just be more explicit here. You don't have to be immediate mode. But yeah, I think we're good. So we are fully architected with the new designs, which means let's see here. There we are. We now have multiple mode field pulled out as a special handler type, We've got memory addresses, all cleverly handled, much more succinct. We've separated our print statements out from our execution. It's a little bit of duplication of code, but it's fine. Our instruction handling, I think, is much cleaner. So our print is now register then format. Our halt is now a multiple mode field. So it can return either the contents of an address or a constant. Load immediate mode, fine. Load, again, memory, it's all working. Memory addressing. So we're down to here. We can start adding arithmetic. We're gonna get a type, and a couple of registers, and a value, a multiple mode value. Just like this. So we've got our masks and our offset shifts. So we're going to do add, then it'll be very trivial to add, subtract, and multiply and divide. They're all the same shape. So add is the only one that we'll really have to think about for a minute. One other thing we could do. One thing I would like to do is to read in a file and execute that. So maybe I misplanned today's string length. Anyways, I'm basically just showing you how you might build a VM that meets our spec with some nice bells and whistles thrown in. Like the print, that is not strictly necessary. Oh, let's see. So that gets into a whole separate chunk of design. It's 2 o'clock. So building this VM might be a little bit of a bigger project than I had initially thought, even if it's a simplified one. That's why we're doing this series of fairly low prep lectures. So I can find out what I need more prep time and less prep time for. So I'm kind of at a point where I would like to write short programs, write them out as files, and then execute them. But things start happening when you do that. We need a way to know if we've opened the right kind of file. Maybe our endianness needs to flip. We haven't talked about encoding a little bit, but this is one that matters. We also have the question of versions. Since we're going to be updating our virtual machine with versions, you have to make sure you're opening the right version of the file you can execute, because we will make sweeping changes to the VM over time. We'll add more memories, more memory, more registers. We'll add different operational codes. So your version number has to match. but I kind of want this to come out of here into a different piece of software. That's a whole different thing. Maybe we do that. We do that. Instead of main, we'll do a byte code generator. We're still a little bit from main here. But not very much. Okay. Hey, Drew Vest. Good afternoon. Happy Friday. Yes, happy Friday. Yes, indeed. Friday is happy. Big plans for the weekend? You know what? Maybe we don't do that at all. Instead, we just say F out, open some file. I'm going to write binary. We're going to call it something. Load store test. Load store halt test. Dot do bytecode. That's kind of it. Do bytecode. Version. DoHVM major. Minor. Patch. Probably good enough. All right, nice. No special plans for the weekend. I'm just gonna relax, I think. Nice. I need to change gears. I'm probably gonna use the weekend to do that. I've got a company I'm running with my business partner, and I think it's time to ramp that up to 100%, which probably means the streaming will be much reduced. Like maybe Fridays only. We'll see. Like I said, I've got to sort of shift gears here. Major, minor, patch. F right. So this is one of those built-in functions we can get documentation for from c++.com. Reference C library, C standard input output, fwrite. Pointer, a size, a count. Oh. Mutate T temporary value. And equals DoHVM major fwrite temp size then count. So size of temp count into fout. Write out major, minor, and patch. And 0. This is going to be our magic number, DOH bytecode. So we have an idea that we have the right file. We have a version number. Next thing we need is actually a buffer. So we just create a VM, right? A DoHVM. So 0 is everything. So DoHVM init our VM. And just write it, right? So let's see here. Fwrite, we want the instruction count. So that would be in VM dot instruction count. Size of that. One of those into fout. VM dot memory size of a VM memory VM instruction count into fout. There. I think that's basically it, except we add all of our instructions here. So in DoHVM H, just grab all these. DoHVM.c, grab all those. Should just be able to use that now. So what is in our main? Basically happens here. Okay, so here's the deal. We create a new VM, we zero our memory, we add these instructions to it, then we create our file, open it, we write out a header value, we write out the number 0, then major minor patch. So we've got two 4-byte values. Then we write out instruction count, which is another 4-byte value. Then we write out our memory, which is this address, this many bytes per entry, this many entries, and then we're done. And this part can be pulled out just a minute. All right, program. So we have a DoHVM and a const ** file name. Which looks exactly like that. That's basically it. Your header, there's your version, instruction count, and your actual instructions. Is that it? So we now have two main functions. We need to generate two programs. So look at our make file. We have that. And we need the bytecode gen is our other main. It's going to go into a tool. Bytecode gen. Now when we compile, you can see that it tries to build both things. Oh dear, we do need those opcodes, don't we? In theory now, I should have a program called bytecode, or Do bytecode generator. It doesn't tell us much. bytecode generator wrote some number of instructions to some file. There we go, wrote 11 instructions to that. Does that look correct according to this? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Correct. So in theory, we now have a file that we can look at called load store halt test. There's DoHV to indicate this is a Do bytecode file. Then we need a version number, which is 0001. So empty byte major minor version patch. Then we have the number of instructions, which is B, which is 11. Then we have 11 instructions in theory. And that's it. So we can output files now without too much trouble. I just need to be able to read in that file and make sure it's correct. So in main, DoHVM load into our VM this program. It does not exist yet. We have not told the computer how to load a file yet. This might get a little bit complicated, but not too bad. Okay. So we're gonna load. We're gonna always start from a known state. So we'll first clear. In, we'll read bytecode. If VM verbose Okay. So we're gonna read our file. So far it's very, very simplistic. So DoHV are these bytes. So instead of printing out, we're going to actually do an f read a word. Size of our word, we're going to only read one of them. From, this is F in, by the way. In. Yeah. Swap endianness equals 0 if our word equals 0x that. We don't have to do anything. It's equal to the opposite of that. Talking about the opposite of that. If you have big endian and little endian, it means that the bytes are the opposite order around. So it's actually 42, 48 for F, 44. This is called checking a magic number. Basically, right off the bat, at the top of the file, I expect these 4 bytes. The odds of some random file having this as their first 4 bytes, especially if everyone is very, consistent about putting a magic number in their program, the odds of you coming up with their 4 bytes is very small. That's why I'm checking these 2 where it's swapped order. Because if it's this, we probably need to swap endianness. Otherwise, that's fine. Otherwise, we do have an error. Oh, I'm in the wrong file. Oops. It should go into here. Dun, dun, dun. We'll undo all this work. That's fine. This one here. Else. Printf error unrecognized file format, and we bail out. Otherwise, we need to read the next value. And the question really is swapping endianness here. So if you read the next word, okay. Read the next word. You got 32T version equals DoHVM. Where are my major DoHVM major minor? Okay. Shifted 16. or board with DoHVM minor, shifted 8, or DoHVM patch. Swap endiness. Let's see here. Endiness swap 4 bytes. Reverse 4 bytes. Which means I need a function called reverse 4 bytes. That's easy enough to write. In fact, now let's just do it as a function. All right, return value. So this is our most significant bit. Downshifted 24. Board with value. Downshifted 16. Downshifted 8. And get the next 2. Those have to get shifted that way. 8 byte bits. Get shifted 24 bits. I think that's about right. Yep. 24, 8 and 8. I think that's correct. So reverse 4 bytes. Okay, then version F1, 2, 3, 4. Bit shifted by 8. This equals DoHVM major. Downshifted 8 equals minor. Let's get our patch version. if all of that together, all of these conditions must be true. If none of those are true, unsupported version. Okay. Next, we read another word. Actually, let's see here. Let's see here. VM instruction count. We have to swap any units, that's fine. That is a signed integer. Therefore, if VM instruction count is less than 0, that is an error. Invalid instruction count. If we get through all that, then what we do is we go for int index equals 0, index less than VM instruction count. F read into our VM memory at that index. VM memory entry, doesn't matter. We'll read one entry from fn. And if we must swap and this, we can. Okay, did that work? Let's try it out. We have a typo instruction count. Let's see how it rolls. Hey, that looks like correct output. So now our virtual machine can read in a bytecode file. We can write a bytecode file. So just one more small change. If argc is less than 2, usage I don't know if I like that actually. It's fine. DoHVM bytecode file. Return 0. Doesn't do anything. It's not a failure. RV1. Hey, success. One thing we should probably do. If bin equals pointer, you can actually check for real errors, but you know, we're not gonna today. Could not open file. Could not open file. There we go. Could not open file. All right, we should check. Load. Start. If VM point to instruction count greater than or equal to 0, greater than 0, then we're running. Okay, so that all seems to be working. We go back to here, and that works. Perfect. Echo question mark, it's 42. Okay, so now to do our testing, we don't use hard-coded values. We can load any file. Perfect, that's good, because we're going to add a whole bunch of stuff. Let's see, let's check around a little bit. See if anything's going on that I need to address. I don't think so. Let's go do some arithmetic. Okay. Our VM is now general purposeized. One thing we want to know. What if we could turn verbose on and off? Or we could do a couple different things, actually. Let's do a couple different things. Let's do this. Options. Options are optional. Parse our arguments. So, for Index equals 1, index less than argc plus index. We get our arg, all star arg equals argv at index. We need string, because we're going to compare. So we need a string compare arg2 dash h or strcomp arg with dash dash help. I've always liked when both of those options are available. So if we have help p print program dash x dash print execution. Dash v or dash dash verbose. There we go. Also means we need void print help. Fairly common pattern. Dash p. I'm going to make a couple of things here. We're going to say int print program. Oh, not v. We've already got that kind of. Print program equals 0. Print program equals 1. Print execution. Print execute. Equals 1. I think that's most of what we want. Print help. Options. Which means we load argv at argc minus 1 every time. Okay, we're getting there real close. Dash h gets me here. Dash dash help dash h. With this help message and exit. Do exit. Dash print program dash p. with the program before execution. Execution, execute. Instructions during execution. That will be handy. We need a bytecode file. Okay, so I think this is much better. Load. If print program if vm dot verbose equals print execute. I think that's basically it. Oh, if do exit. Print help. If do exit. Print 0. There we go. Parse art. Create a virtual machine, initialize the virtual machine. If print program. Or print program. There we go. Program some number of instructions. VM dot instruction count. For its index equals 0, next less than VM dot instruction count. DoHVM print instruction. VM index. DoHVM C start VM verbose. Executing. Right, let's take a look and see how that goes. RC. RC undeclared. Oh, oops. Let's have to cast that. Not sure why we weren't. RC RV. There we go. Okay, so we should be able to run that. We can run -p to log the program before we execute. There's our program. We can run -x, which inlines it with our stuff. One thing we do want we can actually run both of these -p -x. There's our program, there's our execution. Bytecode generator. Here's kind of a fun thing we can do. We can say run means we build all, then we run this, oops, command, and from this command, make all make run. Make sure the compile happens, does the program, does the execution. Error 42, but that's okay because make oh, no, that's perfect. We expect error code 42. When we halted with $2, it is 42. So correct. Agreed. We actually don't even have to do the echo $question mark because make will tell us it's not a 0. So there you go. We can now do all kinds of things. Main.c. -h should mean that literally nothing happens. Nothing happens, prints the message, and exits. Perfect. Code gen. Run. There we go. That's better. Wrote 12 instructions here. Print out help. If we change our make file again, just to make our life more convenient. Run. Boom. 12 instructions. We do have 2 halts, but one of them will never be run. Oh, that halt is wrong. Because it's It should be 13. What's the other halt? What is the other halt? Plus 63 is that. So y is print instruction halt. Print UMMF. Signed value. Value with unsigned value. Halt, however, can be signed. Nope. Last one is int 8t. Signed MMF. There we go. Boom, halt, that is wrong. It is plus the 63, so we did not minus the 63. I changed it. 76. Signed multiple mode field. Maybe not subtract the minus 63. Yep, that's the problem. Run error 42. So if I swap the order of those two, if I go to what is it? I'm sitting here trying to make sense of using Python for backend dev. Yeah, I was always a little puzzled by that. Like, the assumption is backend should be fast because it's going to service a lot of traffic, but Python is not known for being fast. So I don't know. Maybe I'm missing something, or they've built enough Python libraries on C that it's okay because the performance critical sections are just really C code with a thin Python wrapper. But yeah, Python itself as a backend, ooh, scares me. So I swap the order of these two. We should get error code 13. This should say halt 13. Yep, perfect. Oops. Okay, so our VM can now do everything we want. DoHVM first Emit, load, store, nope, and print are working according to the ISA. Print program, print execution, help, all available through CLI args, reads a Go bytecode file. Oh, right. I want this global. It's not always this account. So the discourager of hesitancy at Gmail. Good go. Star.o, star.exe, star.log in case we get around to it. Oh, that's much better. I suppose we don't want the DoHVM files either. Most of the time, we can just generate them again if we need to. There we go. Where are we at? 3 hours in. We have. So let's see here. I guess I'm what, 5 hours in on this VM roughly, in rough numbers. So if I was a high school student, oh, word count lines, the files. I'm what, 650? What if we put star.h? 700 lines of code, 5 hours, and 100 lines of code. See, maybe it's me. This, one of the reasons I'm kind of running through this series rapidly is I kind of want to have an idea of scope. If it takes me 750 lines of code in about 5 hours, what would I expect a college undergrad freshman to be able to do? I would expect to have to give a lot more details and let them discover a lot less. We haven't even started implementing our arithmetic operators, etc. But this is kind of where I would want their program to be for the first assignment. So maybe this is like a 2-week program, because they would have other classes. I would expect them to take, a freshman would probably take between 4 times longer, about 4 times longer maybe, a beginner, with some office hours. 4 times longer, about 20 hours, 10 hours a week. It's not too bad. I've had way worse assignments. So if it takes them 2 weeks to get to this point in their development, adding the other stuff is actually simpler. Adding arithmetic, bitwise operations, comparisons, logical operations, and then we'll do the branching, jumping code. Could do 2 of those and 3 of those over 2 weeks. That would give anyone time to refine fix things as they go. Interesting. Trying to kind of scope this out. So this is a 2-week assignment. Another 2 weeks. Maybe another week. So we're talking 5, 6 weeks. How long is a semester? How many weeks in a semester? 15 to 17 weeks. Now, most of my classes as an undergrad, I could even go look at them probably, would have very low line counts, but they were like once a week. So maybe 2 weeks to get to here, 2 weeks to add some more opcodes, 2 weeks to add more opcodes. So that's 2, 4, 6. 2 weeks of intro material, 8. That's like half your semester right there. And maybe longer than that. I'm just trying to think. -v -version. This one doesn't actually need anything special because we can just get to it. Print the version number. Run it. All right. DoHVM version, whatever, no new line. Let's forget that. Someday I will not forget. DoHVM version. Oh, come on. There we go. DoHVM version 0.01. 12 instructions. Here they are. Here's the output. Asterisk return. Number 10 in hex return. The error return code is 42, which is expected because of this. So yeah, I think this is where I would expect a student to get at the end of their first major program. Hey, Seacombs, how am I doing? What are we working on? Let's see, complicated. I'm running through a series of lectures that I've semi-built in my head. So they're crappy. Like this whole week, I've just been kind of rushing to get a few slides done. and then present it the next day. Sometimes it's like an hour, sometimes it's 2 hours, which means I probably need to split that lecture into 2 parts. And I'm kind of taking notes of what I did, what the structure needs to be, which is mostly correct. And then I need a lot more, obviously, instruction, a lot more like details and examples, but it's like a beginner series of programming. Right now, so here's kind of my overall syllabus, I guess, that I'm coming up with. I think you need about 2 weeks of introductory material. I think I could do a decent job of getting through most of that material in about 2 weeks. But then it would probably take them another 2 weeks to get through to this point. Another couple weeks to add more opcodes, a couple more weeks to add more opcodes. And that leaves us with a few more weeks in the semester to build interesting programs with a very simplified virtual machine, which they built themselves, right? So let me added version printout argument. So let me see here. So I wrote up an ISA for this virtual machine. There's actually kind of 2 parts here. Let's go to the start of the VM design. So we kind of talk about virtual machine. Here's the structure we're going to use, blah, blah, blah. You have a kilobyte of memory. You have 16 registers. Register 0 right now is reserved. Instructions are 32 bits, 12-bit opcode. Here were the first operations. I've already made changes since then, so this slide probably needs to go away and just reference the instruction set architecture, the ISA. And I think, now that I've gone through and built it and documented most of it, I think this is a reasonable starting point to architect a very, very simplified virtual machine that you can write even as a beginner programmer. So I'm thinking, yeah, about 8 to 10 weeks to get a virtual machine up and running for a new programmer. So finish up this lecture, then basically go back and refine all the early lectures and learning plan. That's kind of what we're doing. So the question is, are we ready to add arithmetic? Are we ready to add arithmetic? Right now it's just register based and we can load and store and print, and that's it. So we're just about at the point of needing to add, add arithmetic, bitwise operators, etc. Yeah. But I'm trying to derive the requirements for a halfway decent virtual machine. My overall long plan would be the beginner class would build their own virtual machine and solve some problems with it. And then the second chunk would be, let's build a very, very simple language which outputs the bytecode for your virtual machine, and then make some interesting programs with that. So that would probably be a full another semester all on its own. And then part 3 would be optimization. You could optimize the virtual machine, you could optimize the code, bytecode that your compiler is outputting, like just make it better. So there's a lot of room for a new programmer to learn, because this chain of 3 sections would be a large scale project, which is something beginners don't get, right? Most intro programming courses, their assignments are between 1 and maybe 2 weeks. So the idea is, sure, there's a couple of toy ones during that first couple of weeks, but as soon as we start in on week 3 of the course, it's serious. This is all stuff you're going to use over the next couple of years, or year and a half, as a series. So what is simple is gauged differently from an experienced coder to a beginner. Yep. Which is why I'm running through this once badly, very badly. This lecture series is not good yet, but I'm running through it, and I'm taking mental notes and then writing them down later. Here's an area where I need to explain more. Here's an area where I forgot to explain this. just today I was like, oh, I should explain that. I should explain that in my head. So mostly just making it real, right? If you have a design and a plan and you think you know what you're doing, it's not real until you put it on paper, you put it, yeah, and you give the presentation, right? Then it becomes real. Then you're like, oh, here's all the things I didn't think about. So I agree, it's not the same for an experienced programmer to a beginner. So getting to this point where we're at now, where I've implemented, I said it was around 750 lines of code. Where is it? This thing. Yeah, around 750 lines of code. This took me about 5-ish hours of just sitting down and grinding, right? And I would not expect a freshman to be able to grind through this much code in 2 weeks. I would expect it to take, well, not in 5 hours. 2 weeks, maybe, but like we'd be doing specific classes on here's this part, here's this part, here's how you do this with code, and a lot more detailed design. So that's kind of what I'm doing. It's not real until you make it. Then you can reverse engineer your requirements from that and your lesson plan from that. So, so yeah, thanks for being my guinea pigs. And a few times people have pointed out, oh, you should mention this. I'm like, you know what, that is a good point. At this point, I should mention that. So just getting some ideas, because I don't like the way computer science is taught mostly, at least not early computer science. I think building your own virtual machine, building a compiler on top of it, and it doesn't have to be good, it doesn't have to be fast, doesn't have to be well designed, it doesn't have to be featureful, but you build those parts and your understanding of the whole system just deepens. And early on, what you need is some project to work on. That's the hardest part. What project do you do to learn? And I think this series would be very, very beneficial. So I don't know. Just a thought. Like I said, I'm not good at this yet, so this is just a first stab, fast, dirty, and see where we get to. But the virtual machine is working, so if I look at let's look at a piece of code just to show you. This is the load store halt test. I'm going to reread it. And we're back into hexel mode. There we are. So first we get our 4-byte magic number. Then we get our version number, so that's a 0, then major number, minor, patch. So when we read in bytecode, it has to match the version of our virtual machine, because as you go through the course, we'll add more features to the VM and show how it changes the code, how it changes your efficiency. Then we have the number of instructions, which is 12. Then the actual instructions are the rest of the body of the file. So very simple bytecode file format. Each instruction is 32 bits, so we don't have to think. Yeah, just kind of fun. So I'm kind of debating what to do next, though. Because we've got the DoHVM opcodes. These are the opcodes we still have to implement. We actually have to implement a few more. So there'll be the branching, jumping. But once you have these, once you can load and store, do arithmetic, bitwise comparisons, on logical, and branching and jumping, that's what you need to have a very minimal virtual machine. So we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22 opcodes. Logical would be your logical and logical or, and your logical not. So that's 3, which isn't hard. Branching and jumping, you have a jump relative, a branch, a go-to, so basically an absolute jump. So jump I think of as relative, a go-to I consider hard-coded. Then you have branching, so branch if 0, branch if not 0. And initially we wouldn't do anything fancy like branch predictions, although that would be fun too. Like I said, during the optimization phase in that 3rd segment, that would be where you really get crazy. Like you'd learn about caches. We'd actually implement a cache in the virtual machine, and things like that. So start with a small VM, build it up over a year and a half. Could be kind of fun. So yeah, long-term plans, definitely early days. Like I said, I kind of sat down each morning or night, slammed down some quick slides. I think the structure is good. But anyway, so that's what we're working on. So add, subtract, multiply, divide. Should not be hard. Let's just do those ones. Let's add those. We've already stubbed them out. So when we go to op add, so I'm going to look at the setup here. Here it is. Op add, we get 4-bit type. And we've talked about type up above, so we'll have to look at that. A register, a multiple mode field, and then a destination register. I think that's it. So, with the documentation reasonably well talked about, let's go do this. We're going to grab the type. Data type, get the field. Then we're going to get register A, which will be here at that. Register C is simple. That's just this with no shift. Then we need a multiple mode field B, which is this. With those things, we should be able to get what we need. So we have to switch on data type for this to work. And data types we've defined in our document. Type. So far, we're only going to support int, uint, unsigned int, and float. Maybe we'll add boolean later or something. Not sure. So data type names. one thing we do want is this. DoHVM type int uint and float. For now. I think things are going to get a lot more fun when we get to things like strings and so forth. Okay. Add. Switch our data type. DoHVM type int uint float default. I don't know what error codes mean anymore. Invalid data type. Okay. If we are an integer, what we're going to do is we're going to say VM at registers RC equals VM.2 dot int registers sub RA dot I plus, here's where things get a little bit interesting. Oh, interesting. Oh. So here's something I need to add to the documentation. This is, like I said, why we're experimenting here with this. So come over to here, show the browser, not this one, this one. When we add, note if type is float, MMFB must be an integer. MMFB, so multiple mode field B will be considered as a 16-bit signed integer, or an 8-bit as a signed integer which will be passed to a float for the computation. Okay, so we'll treat this as a float, we'll treat this as a float. This one will be read as an integer and cast to a float. So that'll give us our plus, our minus 63 to plus 64. So that's something we do have to document. Okay, like I said, we're learning as we go. Until you've implemented it yourself, you shouldn't teach it as a course. So plus, let's see here. There's a function for this. We want this as a signed MMF. VM MMFB, and I think it's true or false if it's a thing. Okay. At this point, we don't care. Plus a value. int 8t, so a b as int, uint 8t, b as an unsigned int, and mmfb. We'll give it a name, even though we don't need to. B as a register. So our so this one is signed. mmfb. This is very similar, except in this case we're going to treat everything as unsigned integers. We have that union there. This one will be a ummf. Float, however, take this and we'll treat it as a float. We're going to pass it to a float. I think that makes the most sense. Then we need to be able to print all this. Print the instruction. Here's add. Let's see here. So data type fits here. R sub A we've already got. R sub C we've already got. That's mmf. So I guess we need u mmf. Okay. So our data type. Here's our RA. ummf. C. Printf add. Modulus, let's see, $sign modulus u plus DoHVM add. This is a DoHVM type names. Let me add it somewhere. Where did we put that? Data type names. Of our data type. And our register plus something, ummf. This depends on the type. So here we need to switch on data type. Case int int and float will be identical. type uint. Right. So if this, that's how we extract our field. RA and RC are easy. It's the actual multiple mode field that gets complicated. We're going to add blah 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 and print. Then we print that we output this all to $sign register C. I think that is an add. Remember code generator. Void right load store alt test. We're just going to take a pointer to a VM. We'll write out a simple test of load store halt. Arithmetic test. There we go, init. We shall load in a number 420 and register 1. We shall load another number. Let's see here. Let's make it interesting. 246. Into register 2. And then we'll add them, which is the thing we don't yet do. Add and add. Now this one might be a little more complicated because we're going to say we're going to add register 1 to 2 and store it in 3. Then DoHVM print or add print RVM register. Oh, fun, 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 fun. Oh, put that in the register 15. We do our prints. Print. There we go. Print one as an int. Okay, so what are we doing? We're trying to write some bytecode here. So we're saying store in register 15 the value for new line. Then in register 1, we're putting 420. In register 2, we're putting 246. We're going to add registers 1 and 2 and shove that into register 3. I will print this, the value of register 1 as an integer. We actually need here the DoHVM type int. So it treats them all as integers. Int char 15. We're going to do a DoHVM add load immediate into the VM at register 14, the plus sign. I think we're going to use these over and over again. 14. We'll put a space. I also want an equal somewhere. 13 equals. Then 12 will hold our operator character. Register 1, register 15, register 2. Well, not 15, we want a space. So this is 14 as a character. So this is register 1 plus space plus register 2, or plus. I want the plus here, which is 12, then 14. And then 2. So this is print register 1, space plus space, register 2, space equals, space is the next thing, 14, space equals 13, 14, and then we print out register 3, and then we output our new line. That's how in assembly code, or something like an assembly code, we write out a simple addition problem. Part of me wants to extend an operator here. Go back to our browser, go to print format, $1. We have 16 bits. We could do more. So instead of this $A, we could make this one of those multiple mode things, because that would actually get us our entire ASCII. If we had a multi-mode format, multi-mode field here instead of just a register, which would make printing individual characters much more efficient. Ooh, that's handy. Oh, do I want to do that now? Part of me kind of wants to. It makes writing string constants much easier. Time for you to go. Have a very nice weekend. Don't eat too much cow meat. But I love cow meat. You have a good weekend. We'll see you next week. Thanks for dropping in. You have a good one. How much suffering am I willing to do here? It really probably isn't that much. What if we put format here? I like the idea of not wasting as many bits. Format. Delete. Split cell. 1, 2, 3, 4, 5, 6, 7, 8. Incorrect. What happened here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Oh no, we have to split it into 12. Dadgum. That's not gonna work very well. All right, let's go grab a blank table. Go to print. Drop in our new table. So this will be FFE format. Will be these 4 merge cells. Format. We'll have that, but then we'll have 1, 2, 3, 4. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. I really wish it would stop doing that. 4, 5, 6, 7, 8. Merge. So that'll be multi-mode field. Fill it with orange. This part becomes unused. All right, not a big fan of this. There we go. Merge cells. Mark it all as gray. Unused. Delete the old table. Okay, so format now is at bit 16 to 19. And it shifts 16 bits. MMF. Oh man. We still have bits. We still have bits. Nope. We're just gonna put on here. I want to, but at this point, I don't think it's a good idea. Field, multi-mode field, 8 bits from bit 8 to 15. And it needs to shift down 8 bits. I wonder, I could print 2 values with a single instruction if I reserve 1 bit of format for 2 prints or a single print. That leaves me with only 8 format codes, and I've already used 5. Let's not overthink it. Let's just use 1 MMF. Okay. So, as we change our ISA, that always requires a good number of changes, which is a little sad, but this could save me a lot of headache. So op print There it is. Okay. Format gets these 4 bits now. So instead of a register, we get an MMF. 8 bits worth. Depending on the format code, I have to use one of these. Int ht signed MMF. This depends on the format. This won't work with float. It can. Again, if we treat it as an integer, which we cast to a float. So UMMF. So basically, U and X. C can also be unsigned. If it's a register. I'm gonna have to think about this a little bit. I just bite off more than I feel like chewing right now. I don't think I feel like doing that right now. I don't feel like doing it. Do I? I'm almost there. I got most of it. If it's a uint, a hex, or a character, we do this. Otherwise, we do that. Okay. Now instead of this is a register, then UMF equals the value of the register. Okay, I think we have to do it this way. Great. The float we have to treat a little differently. So if it's any of these, we kind of don't care. If it's this, we do that. This, we get this as a float. Nope. Float. Otherwise, float equals SMMF. I think UMMF, UMMF, UMMF. SMMF. Float. I think we've just opened a can of worms for testing. I'll take this one out for now. Add print register and format are now different. So this is format is here. Register is going to be bit shifted 8 bits. Otherwise, it probably doesn't matter. It's how we set that. Bytecode gen, add a print. This needs to be register mode. Oh. Okay, I think we're good there. One last thing, print instruction. Print. It's not R sub A. Oh dear. This is one of those things where I have some regrets, maybe? So this is, SMF or MMF. Signed, unsigned. Yep, all very unfortunate. Because we've added some complexity here. Hmm. So we get our format. If it's a uint or a hex, we do this. So there are differences here. $sign U. So we're just printing a register in that case. Otherwise, we're printing $sign U. This is going to be similar. Okay, so if it's a int or hex unsigned, we do that. If it's a character, we only get the 1 byte. If it's an integer, print that. Now we print it as modulus D. If it's a float. Reg undeclared. int 8t data type, register A, register B. Oh no, this is a MMFB, register C. Or our data type, bit shifted 16, or register A, bit shifted 12. Or MMFB, bit shifted 4, or register C. Which is a little bit awkward. We save. Do that. Is that add and add instruction? Okay. I think we're crashing. That's probably my own fault. Or clock. This seg fault. Nowhere helpful. Not sure about this. Hmm. Hmm. Dash V should print something before we even get anywhere. Oh. Guess we just do this. Flush. There's that version. All right. I don't think I need these here, but it's fine. All right, program. Load store. We'll upload store print. Okay. All right, fit. If it's uint or hex, we get the field. We print either a register or the number. We can simplify this, can't we? That might be part of my problem. Nope, still not my problem. Huh. Oh, I know what's going on. Oh wait, do I? Data type. This isn't even the problem, it's the print statement, right? Print. Oh. That's why. Sheesh. Where did that go then? I had it just a minute ago. Print types. There we go. Okay. So now print character, blah, blah, blah. Okay, so that all sort of works. That works correctly. And gen. In here, we no longer need this stuff as registers because we can say print register mode 1. Space. Oh, this is so much better to read. Equals space register 3 new line. Oh, that's better. Much, much better. Alt with a 0. And anything else I need to do here? Not really. Cool. Arithmetic test. Okay, that all looks fine. DoHVM exe -v -p arith. Oh, I had this commented up. Okay, 14 instructions to arithmetic test. Dum, 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 dum. -92 plus -10 is 103 is wrong. 420 doesn't fit in a byte. I can't load that value. Oh wait, I can too. 420 should fit just fine. This add is wrong. Int $1 plus that $2 should be there. Oh. This one has to have the mode specified. Yeah, $1 plus $2 yields $3. Load immediate. I should have a 16-bit value I can load in here. But printing the characters works. Print 1, print 2, print 3, space plus space, space equals space, new line character. Perfect. Print it as an integer. What if we print as unsigned int? I'm just trying to figure out where we've gone wrong here. U2 is undefined. Oh, well, that's closer. It's wrong, but it's closer. So load immediate is not working the way I expect it to do. Let's go debug that. Well, is indeed a 16-bit value. Huh. Load I. Four 246. What happened to 420 here? I don't. Oh, this is interesting. Oh, option. Okay. Put a break in. Print as uint the contents of $1. If it's uint hex or character, we get the U unsigned version. We'll resolve the value. If it's an int, we get this whole thing. I'm so close to having this just working. But it isn't working. Why is this not 420? $420 modulus 256 is 164. So somehow it's getting truncated to just a byte. $164 plus 246 modulus 256 is 150 cents. Where's this 166 coming from? Modulus 256. Nope. I'd like it if this value just wrote out the right value. What's going on here? 420 shouldn't be that hard. Hmm. 420. What have I done wrong? Let's see here. Print registers of our dear old VM. Here 2D. Let's just do that. Why? Print registers. Of our VM. There we go. 14,246. Okay, so we have a couple things wrong here. $420 and 246 are indeed loaded correctly. So there's something wrong with printing here. 2. This is the incorrect output. That should be 666. That's not even that. I don't know what's going on with that number at all. Correct value. Wrong value. I know how much this one is off, but I don't know why it's off. This is a register, so we have to dereference the register and get that unsigned value. Oh, because SMMF. Okay, I got it. Oh, it's 32P. Signed integer and unsigned integer. This is the unsigned integer. If it's a register, we can do that. This is the signed integer. Otherwise, we put the SFMF. If the case, going to do that. Otherwise, we take float of SFMF. UI, signed I. That should help a lot. 420, 246. Okay, so our addition is still wrong. And at least our printout agrees with that. We were truncating before. 422. This whole MMFB problem. I'm not actually resolving this. The UMMF. These are backwards. Signed MMFB, signed MMFB equals that. Unsigned. Unsigned. No, let's be signed. Then we need what's this B sub I? B sub I. I'm not using that. Signed integer. Unsigned integer. So this is a signed integer equals. If this is true, then it's a register. MMFB. Otherwise, it's just MMFB. Unsigned. Unsigned. Unsigned, unsigned, unsigned. Unsigned integer. Oh wait, this is signed. There we go. If we resolve the multi-mode field, if it's a register, we take the register there. Note. Dot unsigned. Dot integer. There we go. All right. Conflicting types. 293. There we go. Hey, there it is. 420 plus 246 is 666. Registers look correct. Means we can remove that now. Heyo. Nice. So we've got addition done. Well, done. We should probably... I would like to do floats, but I don't have a good way to load a float just yet. We need some bit shifting operators for that to work. Okay. We got add done. It's not great, but this is the same pattern for subtraction and whatnot, so it's not too bad. DoHVM. Subtract. Same thing, but minus. Might as well do multiply and divide, right? We're not doing any error checking here just yet. Okay. Add a subtraction. We're going to subtract register from register 3, register 2. That must go into register 3. Register 3 minus register 2 should be 1. Multiply register 1, register 2. Oh, not into 1. I'm going to put that in 4. I'm going to put this one into 5. Give register 3, register 2, and put that into 6. Whew, okay. So this is the subtraction that we want to do. We want to get 3 minus 2, which ends up in 4. We want to multiply registers 1 and 2, and shove that into register 5. And lastly, we want to divide 3 by 2. And put that in register 6. That should be integer division. All right. Let's see how that goes. Tum-tum-tum-tum. Implicit declaration of add sub O. All right, add sub. Multiply. Multiply. Divide. Okay. 420 plus 246 is 666. 666 minus 246 is 420. So we agree. 420 times 246 is 103,320. So that's correct. 666 divided by 246 is 2. So cool. It's working. Our program's getting a little long because the printout's so bad, but we basically implemented arithmetic. We don't have floats yet. But that's register arithmetic. There's a lot of different ways to slice and dice your arithmetic. So, in fact, we could do this a little bit. Gen, where we do the divide. If we don't divide by a register, we just divide by the number 3. Well, let's go back to here. Immediate mode 3. Just because we can. Let's stop printing out the program. I don't think I need these to be flushed. Boom. Okay. So 666 divided by 3 is 2. That's definitely not right. Everything else is correct. Uh-oh. 666 divided by 3 equals 2. It's not 2 unless I made a mistake. 6. Register 3. Oh. Divided by 3. Okay. Do that in both locations. Both of them are printing and we're not printing. Divided by 3. Oh no, this is terrible. Register 3 divided by absolute 3. Shove it into 6. Register 3 should have 666. So this should be 111. Register 3 divided by immediate value 3 equals the contents of 6. So maybe a little goofiness around the divide. Yeah, this doesn't make any sense. Oh, we're not printing out these correctly at all. That's something we should do. Wherever add is. Subtract. Multiply. divide. These all have the same shape. Oh. Plus. Okay. $3. Oh. -3, -60. What does that even mean? That's not -60. Let me go to the div. SMMF, UMMF. Hmm. Okay, well, two problems. This automatically happens. That's not going to be happy. Think. Partner 2. That's still wrong. Not sure. Still have some debugging to do on this little teeny virtual machine. All right, well, we're probably going to call it there. Everything except for division, well, I'm assuming all of these would also fail with a constant value. We're not really type checking a lot of things, not type checking, but range checking things. Print, what if we did this? Gen, let's go to uint, just go, oops, int. So we're adding these integers. Let's run everything. Okay, that is different. -11 is close to the right answer. This is correctly printed, so -60. I don't like that. I should just say 3. I should just say 3. Instruction. Hmm. Or bytecode generator? It's 63 in here anywhere. Add halt. Okay. Oh, doggone it. MMFB could change. That's the thing I will have to do. MMFB. MMFB. All right. Very consistent of me, at least, right? I'm gonna have to generalize things a bit here. It's getting complicated enough. So maybe. There we go. That's the result we expected. If we print the program, divide 3 by literal 3, stored in the 6, we get the correct output. Yeah. Phew. Okay, so we're partly there. Mostly there? We're looking good. All right, cool. Status. DoHVM exe.stackdump. Probably should ignore anything that ends in stackdump so that it doesn't go anywhere. Added arithmetic operations. Instructions. Not tested for float. There we go. I'm going to call it there. You have a wonderful evening, wonderful weekend. We'll see you some other time. Bye-bye.